Thank you very much. Thanks a lot to the organizers for organizing this wonderful conference. So I gave a similar talk at geometric group theory conferences and also at geometry conferences, but I never felt it's quite fitting because it's in between. At this conference, I think it's just right. It fits this description beyond Riemannian geometry. So I want to talk about waist inequalities and Kazhdan property T. And the talk is based on a paper with Uri Bader, actually a quite short paper. And I want to start by introducing what I mean by the waist, or by the lower bound on the waist. So we say that, let's say, a d-dimensional closed, could also be finite volume, Riemannian manifold has n waist, at least omega, if for every map and here you have some flexibility. So depending on how you really precisely formulate the notion of volume, it can take smooth maps. Sometimes it's formulated with generic maps. Everything I say works with real analytic maps, but there is some flexibility here. From this manifold to Rn, so let's say F m to Rn, there is a large fiber in volume. So there is a point in Rn such that the volume of the fiber, so this would be the d minus n dimensional volume, has a certain proportion of the volume of the manifold. So it's bigger than omega times the volume of the manifold. And the very first theorem about the waist is the famous waist inequality for the sphere by Gromov. So he proved that if you have a round sphere, so the picture, let's draw a picture here. Here's the round sphere. And you have a map to an Euclidean space. So let's draw just the real line here. Then there is a fiber whose volume is, well, and you can very precisely say what it is. The volume of the fiber is at least the volume of the d minus n dimensional equator sphere. So let me write it out. Sorry, not MD. It's now the round sphere. So for every map from SD to Rn, let's say n between 1 and d, there is a fiber such that the volume of this fiber is the volume of the d minus n dimensional equator sphere. Yeah, so the omega is the quotient of the volume of the d sphere and the volume of the equator sphere. Now you somehow shift the perspective.
If you're normalizing by the volume, do you not want to normalize by some power of the volume to make it scale invariant?
So I'm looking at the standard sphere, round sphere.
Just in the definition.
No.
Okay.
No. So, and you will see, yeah, okay, I think you will see why because, okay. So, let's shift the perspective a bit from having just one manifold and looking at a waist inequality to a whole family of manifolds. And I'm also not so much interested anymore in precise estimates. So let me define the following notion. A family of, let's fix the dimension, d-dimensional closed or finite volume Riemannian manifolds. Let's call the family F. Has a uniform n waist. Yeah, if every manifold in this family has n ways greater than epsilon, epsilon does not depend somehow on the individual manifold, just depends on the family. So if there is an epsilon, such that every m in this family has n raised at least epsilon. Yeah, already said. And this notion, depending on which families you look at, so the families that we typically look at are coverings, finite covers of a fixed Riemannian manifold. And this notion was very much studied, I would say it was very much studied before the Riemannian context in the simplicial context, because this notion is somehow the Riemannian analog of what's called topological expanders or high-dimensional topological expanders. And I don't want to get into much into that because that's not the topic today, but what a topological expander is, it's also a family, but now it's a family of simplicial complexes. And you also look at maps from the simplicial complex to an Euclidean space, do the same definition, you just have to replace the volume. And the way you replace the volume is you're looking, instead of the volume of the fiber, you're looking at how many n simplices hit the fiber. That's your measure somehow. So number of simplices instead of volume, but then it's the same definition. And this is this notion of topological expanders. And I would say was studied somehow much more before the Riemannian context.
So what exactly do you mean by a family of those manifolds here? So it's just a set of them?
Yeah. Yeah. Right. For now, it's just a set.
And they have different topological types, right? Otherwise, it's...
Yeah, I mean, in this talk, it will be always the family of finite covers of a fixed Riemannian manifolds.
Okay.
But I mean, you can introduce this notion more generally. Yeah.
What's the volume in the simplicial case on the right side? It's the number of simplices?
So you would look at, say, n-dimensional simplices mapping to Rn, for example, and then you could just look at the number of n simplices. Yeah. Somehow in the simplicial, you can always cut at the n skeleton for this notion. But otherwise, it's the same notion. Now, here is a theorem. Let's, I'm not sure how to put a name here. Let's say it's classical. That if you look at the family of finite covers of a Kazhdan manifold, in the sense, yeah, a Riemannian manifold with Kazhdan fundamental group, and I will introduce this notion, then you have a uniform one-waist. So the family of finite covers of a closed Riemannian manifold with Kazhdan fundamental group has a uniform one-waist. And okay, let me just draw a picture. So if you have, not giving a full proof, but somehow, what is the idea? So here is somehow one of these finite covers of a fixed manifold M, right? And you look at maps to R. And what you use to prove this is that a consequence of this Kazhdan fundamental group is that the first eigenvalue of the Laplacian of every such finite cover is bounded uniformly. And then the point x that you pick is roughly the point that divides this into 1/2 of the volume. And you take this as the fiber, and then that this fiber has enough volume is a consequence of the Giga-Busa inequality that relates the lambda 1 with the Giga constant. So it's quite easy proof. And now we looked at generalizations of this theorem. And the theorem I want to talk about is the following. Which is almost the same. So the family of finite covers of a closed Riemannian manifold with Kazhdan fundamental group has a uniform two-waist. So there is an extra dimension somehow that's coming for free. And so the proof is, I think, fits very well this conference, because somehow this is still kind of differential geometric proof, if you want, about the one-ways. But this proof is really quite different, and at the core uses some things about functional analysis of Banach spaces and linear integer programming, some optimization results from that theory. And so it came actually as a surprise. So when we started working on a theorem, we were looking at locally symmetric spaces because we were motivated by a notion of higher property T. And we thought you need this notion to prove such a theorem. And it was actually a surprise in the end that the only thing that you need is Kazhdan and nothing more. And this is a bit surprising because it took actually quite a while to construct two-dimensional topological expanders in the simplicial context that have uniformly bounded degree. So in the simplicial context, this is the work of, let's say, construction of two-dimensional bounded degree topological expanders was by Kazhdan, Kaufmann, and Lubotsky, I think around 2018. And it used some very specific construction of Ramanujan complexes that have a much stronger property T. But here it turns out you only need the Kazhdan property. So what I want to do next is I don't want to assume Kazhdan, or what's also called property T. I will introduce property T now. But before I do, for those who already know, I want to just point out that in the case of the one waist, we used somehow this fact here. And for the experts, so what you're using is property tau. You're not using really the full power of property T. Whereas in this theorem, I mean, not completely sure to what extent you can even loosen the condition, but somehow the proof at least really uses the full Kazhdan property T. All right, so let me introduce Kazhdan property T, or just Kazhdan. I will use Kazhdan property T and Kazhdan property T all equivalently. So on the Kazhdan property, so that property was introduced in late 60s by Kazhdan, and here's the definition. So a group gamma, in our context, always a discrete group, has the Kazhdan property if there is a finite subset in your group and some constant epsilon with the following property. So it's actually a property about the unitary representations of gamma. And unitary representation is it's a Hilbert space on which the group gamma acts by unitaries. And here's the property. So if a unitary gamma representation has a what's called F epsilon invariant vector, and should not be zero. And what this means is, I mean, probably can guess what it means. It means that if you move this vector by gamma in the finite set, so for all gammas in F, and you move V by gamma, and look how far is it away from V, it's at most epsilon times the norm of V. So for all gammas in this finite subset. And if you have such a F epsilon invariant vector, then you have an invariant vector. I mean, non-zero. Zero is always invariant. Okay, so if you have like an almost invariant vector, then you have really an invariant vector. And this is a property for all unitary representations. And Okay, little lemma, I should say. Here we're dealing with finitely generated groups. You can always take this F as a finite generating set. So you might always think of F as being a finite generating set. If there is such an F, you can take it to be a generating set. So may take a finite generating set of the group. Okay, so yes.
What prevents F from being empty?
Maybe empty I don't want. Empty I'm. No, it's not empty.
So that's enough of a restriction. So the definition is just F finite and non-empty.
Yes.
Okay.
Yes. Empty now. What is the empty? Let's not take the empty. So, but okay, no, good point. Right, so what are examples of Kazhdan groups? So the thing with Kazhdan property is that it's not easy to give an example that you actually realize as an example immediately. So every statement that a group has Kazhdan property T is almost a theorem. So it's quite hard to check somehow, but without proofs, let me give you an example. So, for example, the most prominent is certainly special linear group SLNZ. And actually any lattice in a simple Lie group of higher rank. So it's not just this one. That was already proven by Kazhdan back in the 60s and was actually the motivation to study this notion. There are also constructions of, there are also many hyperbolic groups, Gromov hyperbolic groups. There's even a random model of Gromov hyperbolic groups that tells you that almost every group has property T. But it's a bit misleading. It's actually, I would say it's more of a rare property of groups. So these random models are a bit misleading. So if you take a group like a Fourier-Abelian group, it does not have property T. So it's not Kazhdan. And this is easy to see. You just need a unitary representation that has almost invariant vectors in that sense, but does not have an invariant vector. And the regular representation that we also discussed yesterday is somehow the right one. So if you take L2 of this group, it has quite invariant vectors. So what you basically do, let's say, to write it easy for n equals 1, the vectors you would look kind of average around the interval. Something like this, where this corresponds to the basis element in this unitary representation corresponding to the group element I in Z. But the invariant vectors are trivial in the regular representation. There are no invariant vectors. Then if you take a free group, since it has an epimorphism onto Zn, it also cannot have property T because you can somehow pull back representation like this, for example, and get a contradiction. So this is also a non-property T group, non-Kazhdan group. All right, so maybe that's enough for the moment. And now I want to look at the consequence for the group cohomology of a group if it has Kazhdan property T, because that also will explain where this extra dimension comes from. What's the origin of this extra dimension? So maybe I put it here. Let me look at the group cohomology of a Kazhdan group. And okay, you can compute the group cohomology from some free resolution of the trivial module. You could actually take a resolution that's basically the cellular chain complex, or starts as the cellular chain complex of the Cayley graph of such a group. So if it's finitely generated, let's say by some subset S, then cochain complex that computes the group cohomology, and I'm interested now in coefficients in such a unitary representation. So with coefficients in a unitary would look like this. So that's the first differential. And this would be like the first chain group of the Cayley complex, and then it goes on. And this is, of course, just V, and this is a finite sum of V's indexed over the generating set. Right? And the differential on this level just maps V to SV minus V indexed over S. So that's the first differential in this group cohomology of gamma with coefficients in the unitary representation V. And now, suppose that, I mean, let's just assume for a second, we don't need it, but it's easier. Let's just assume that V does not have invariant vectors, right? If V does not have invariant vectors, so I denote the invariant vectors by V to the gamma, and you have this property, then it means that SV minus V is bigger than this epsilon, right? So what you get is somehow an expansion property of the differential like that. And okay, if V has invariant vectors, it's also not bad because the differential on the invariant vectors is 0. So what you get from this is, I mean, first of all, you see that the chain complex computing the group cohomology has a topology, right? These are bounded operators between Hilbert spaces, and so the group cohomology comes with an induced topology. Group cohomology is kernel divided by the image of a differential, and somehow you take the quotient topology and you get a topology. The fact that you have a property like that means by the open mapping theorem that the image of D0 is a closed subset in this Hilbert space. So if you look at, so this is closed. Therefore, if you take somehow the first cohomology, it turns out to be Hausdorff, which in general is not the case for group cohomology because the image is in generally not closed, and if you divide out by a non-closed set, you get a non-Hausdorff topology on the group cohomology. But here you get something Hausdorff. And maybe I also put this here. So the theorem that's a bit more general than this fact that I just explained is this theorem by Delorme, probably late 70s, I'm not sure, that at least for finitely generated gamma, this group has Kazhdan if and only if the group cohomology with coefficients in any unitary representation is Hausdorff. And an improvement over this fact is actually you can show it's 0, and it's equivalent. Is 0 for every unitary. Okay, so I can improve this a bit to vanishing. Now, just see. Yes, I want to make another remark. So if you apply this fact here, this expansion property, let's call this star, this expansion property, if you apply it to a specific representation, namely direct sum of permutation representations, you get something interesting. So apply this to the following unitary representation. It's a Hilbert sum of representations where I go over all finite index subgroups and I take somehow the representation that comes from the obvious left translation of gamma on this coset, gamma mod lambda. So this is a Hilbert sum. Of course, this is finite dimensional. This is a finite set, right? So I write L to L2, but it's a finite dimensional vector space. So if you apply this expansion property to this representation, you get something which is uniform over all finite covers of your manifold, supposing that somehow gamma is the fundamental group of a Riemannian manifold now, and somehow the finite covers of the manifold, of course, correspond to the finite index subgroups of the fundamental group. Okay, so what you get is a uniform expansion. Uniform in the sense it does not depend on the finite cover of so let's say in the situation of our theorem, meaning that M is fundamental group of M, gamma is fundamental group of M and it's Kazhdan. So why is that? Well, this is because, first of all, you could somehow compute like the first two differentials also by just taking, I don't know, a triangulation of your manifold M and take here the universal cover of your manifold and take the cellular chain complex and plug it in. Okay, so there's let me say it again. In order to somehow approach our theorem now, let's triangulate our manifold M once and for all. And of course, on the finite covers, I take induced triangulations. And to compute the group cohomology in these low degrees, I could also, instead of plugging in what I get from the KDE graph, I could plug in the cellular chains of M tilde with the gamma action and the cellular chains of one cells of M tilde. Now, if you then plug in this representation here, just this one, then this cellular chain complex or cochain complex actually computes the or is the cochain complex of the finite cover corresponding to this finite index subgroup. Okay? So M bar is a finite cover, its fundamental group is lambda, and I'm saying if you plug just this representation on this side, what you get is the beginning of the cochain complex of the finite cover. So if you look at this carefully and you apply now this expansion property to this whole Hilbert sum at once, what it means is you get a uniform expansion in the cochain complex that does not depend somehow on the chosen finite cover. So that's already something. But when I say uniform expansion, everything is with respect to the L2 norm. So on this level, cellular co-chain complex, it's a kind of obvious norm coming from the cells, but everything was in L2. And L2 is not so good for the geometry somehow, because in the end we want to talk about volume, we want to talk about mass of cycles, and somehow the L1 norm would be much better than the L2 norm to say something. And all right, so that explains a little shift now. I will shift now from property T, which is originally really something about unitary representation, to a kind of property T for Banach spaces, because I somehow want to get statements about the L1 norm. And there was a lot of activity in the last 10 years about how to extend the Kazhdan property from the unitary setting to the Banach space setting, maybe most prominently in the proof of the Zimmer conjecture, where they use somehow property T for uniformly convex Banach spaces. But what we need is L1, and there is a very nice theorem by Bader, Gelander, Monod from 2012 that says if you have an L1 representation, and gamma is Kazhdan, then you have a similar theorem like the one of Delorme. Then, if you look at the first cohomology, it's 0. So what is an L1 representation? This is just some, omega is just a completely arbitrary measure space, and you look at the L1 functions on that, and you have like a linear isometric action of gamma on that space. So that's what I mean by L1 representation. And then you can take this as coefficients, and it turns out to be 0. So it's a kind of property T for this setting. And it's a quite short but very, very smart proof. And somehow the origin, somehow of the extra dimension is now the following extension that I prove with Uri. So in the same situation, let me just write in the same situation. So you have a L1 representation, and you have a Kazhdan property T group. We can say something about H2, but it won't vanish in general, but it's always Hausdorff. Okay. So in degree 1, in this theorem of Delorme, being Hausdorff for all unitary representation was actually equivalent to being 0 for all unitary representation. If you go to the higher cohomology, that's not true anymore. So you don't get vanishing in general, but you get that it's Hausdorff. And somehow, if you translate Hausdorff again into the fact that this means that the differential, and now it would be the differential D1, has a closed image, then you can also somehow translate it back via the open mapping theorem in an expansion property of the first differential. And that's what we're going to do. So somehow, let me now say how this is used in the proof of this two-dimensional waist, uniform waist inequality. So somehow what we get from this generalization of this theorem is kind of uniform expansion of not only this D0 that we already have, but also of D1, and let me maybe write down again. So we're talking about somehow our manifold M with Kazhdan fundamental group. It is triangulated. On every finite cover, we take the induced triangulation, and I'm looking at the cellular cochain complex. And it has a norm. And now I'm looking at the L1 norm coming from the cells or from the simplices. And I'm saying that this result, by kind of similar argumentation as before, leads to a uniform expansion of the differential from degree 1 to degree 2, and uniform in the sense like the constant does not depend on the chosen finite cover. So uniform means over all finite covers. And somehow what you do is you use all this, and then in the end you apply it to this L1 representation. And somehow the fact that you can take all finite index subgroups at once gives you the uniformity over all finite covers. So that's somehow how you end up doing this. Now, yes, yeah.
In this case, what is the measure space for the D1 domain and codomain?
It's the somehow the union of all the gamma mod lambdas.
Union of all the, sorry?
It's the union of all the gamma mod lambdas. Yeah. So when I say measure space, it's really quite arbitrary measure space. It doesn't have to be like Lebesgue measure space. It can be discrete, it can be anything. It's quite general. So you can take such an L1 representation in the theorem. All right. So now we're a bit closer. Let me write here with respect. That's the point now. With respect to the L1 norm, we're a bit closer to the geometry, but not completely yet, because now you have to, in the end, I want to get something actually about Lipschitz singular cycles and not about the cellular chain complex. And I want to talk about volume, so I want to talk about mass of singular cycles. So somehow I have to get there, and the problem is the R. Since the argument comes from functional analysis, everything is about real coefficients and not integer coefficients. So we want to go to integer coefficients to get something more geometric. And this is a part I won't talk about, but somehow there's some easy tools from integer linear programming, which is just a collection of, just a buzzword for collection of some, I don't know, tools that tell you that certain optimization problems can be solved integrally. But you can, that's the upshot, you can replace R by the integers. That's not something completely general. So this wouldn't work in higher degrees. That's something that works in low degrees, but you can do that. And then you can also turn this, which is maybe also more geometric, you can turn this from the cochain complex to the chain complex via Poincare duality. And get, and maybe when I say uniform expansion of the differential, another word, aka this is you have a uniform linear isoparametric inequality here. right? So if I have a cycle here, and which is the boundary of something here, I know I find a boundary whose norm is bounded somehow by some uniform constant in the norm of this cycle here. I mean, that's the same as uniform expansions, just looking from here instead from here. So this is what you get. And so if you apply Poincare duality, like in the very concrete form, you have a simpler structure, you look at the dual cell structure, you get somehow a linear isoparametric inequality now for cycles in low codimension, which is also uniform, does not depend on the chosen finite covers. So I guess this is n minus, sorry, what's the dimension of the manifold? Let's say d. For d minus 1, cellular cycles, and also for d minus 2 cellular cycles, or simplicial cycles. And now finally, you can convert this into by the Federer-Fleming deformation technique into a linear isoparametric inequality for Lipschitz cycles, but now replacing the L1 norm that comes from the basis given by the simplices, replacing that by the mass of these cycles. So you get, in the end, uniform linear isoparametric inequalities for Lipschitz singular cycles. Yeah, in codimension 1 and 2. And now with respect, so this is with respect to L1 norm, and this is with respect to the mass of cycles. And then there is a well-established technique how to get from this to the waist inequality. Okay, so that's very, very sketchy, but this is somehow the scheme. And yeah, so somehow the core is really this, and somehow if you want to generalize this theorem to higher degrees, so three-dimensional uniform waist inequalities and so on, you would need two things. You would need like a higher property T statement here. That's hard because we need this for Banach spaces. But you also would need somehow a way to convert information about the real chain complex into an integer chain complex, and that's also completely unclear. So it's a bit unclear how to generalize this to higher dimensions, but I want to give you in the last 10 minutes, I want to give you an outlook of what could be a good conjecture, and also point to some other work of Ben Lowe and Mikołaj Fracik. So let me see what is, maybe this can go. So somehow the starting point of this project, and I mentioned it before, I think, was to look at locally symmetric spaces, because we thought it might be very specific. And so there was some very interesting development on the simplicial side. I mentioned this theorem, the first construction of boundary degree topological expanders by Kazhdan, Kaufmann, and Lobotsky. And then later, there was this breakthrough by Efra and Kaufmann, let me also put it here. So also higher dimensional topological expanders, arbitrary dimensions by Efra, Kaufmann. It was published last year. And what they did, similar as Kazhdan, Kaufmann, Lobotsky, what they look at are quotients of Breuer-Titz buildings. Certain quotients of Breuer-Titz buildings by arithmetic groups. And you can also take like then quotients, which a whole sequence, which are finite covers. And this gives you, in the simplicial word, higher dimensional topological expanders. And so there was this, and the question is now, of course, as we've heard, there's always this thing that you have something for SLN-QP, so for non-Archimedean groups, and their locally symmetric spaces are exactly these Breuer-Titz buildings. And somehow you always want to somehow have the analogous statement for the locally symmetric world, which would correspond to groups like SLN-Z. And they always try to somehow go from one side to the other, and sometimes, as in this case, this side are the first. In some cases, the first results were on the side of locally symmetric spaces in groups like SLN-Z. But here somehow it was first in the more combinatorial setting of groups like SLN-QP and their, in quotation marks, locally symmetric spaces. But the question is, what would be that theorem on the Riemannian side in the context of locally symmetric spaces? And one conjecture, maybe I should question. Let's say question, because, but somehow I think it should be true. So here is a question that somehow would be the analog of the Efra-Kaufmann result about higher dimensional expanders. So let G be a simple group of higher rank. Think of SLNR. Of rank, okay, let's say of rank R. And let F be the family of locally symmetric spaces modeled on G right? So this means this is F is G mod K, K maximal compact subgroups, and gamma is a lattice. And to have a manifold, you probably want gamma to be torsion-free as well. So let's say torsion-free. And then the question is, or conjecture, then this family satisfies a uniform, or has a uniform, I think I called it like that, has a uniform R waist. So like the smallest example is a group like SL3R. This has rank 2, so it has property T also, and somehow then all the locally symmetric spaces would have a uniform 2 waist. And that's almost the theorem that we prove in the more general context of arbitrary manifolds with Kazhdan property T. The only difference for R equals 2 between this theorem and this question is here the uniformity is over all lattices. No, I think you can take finite volume here as well. Yeah, should be able to take finite volume as well. But even if you say, okay, let's just do it for co-compact. That's a good point. Then that theorem is not 100% gives you that, because here it's the uniformity over finite covers of a fixed manifold. This would be like uniformity over lattices that are nested as finite index subgroups in one fixed lattice. And here it's the uniformity over all lattices. So there is a small difference, but somehow this small, I mean, I'm not, okay, not sure how small it is, okay, but there is a difference, but okay, so in ongoing work with Uri Bader and Ben Löwe and Mikołaj Fracik, we're trying to somehow get this conjecture for R equals 2 in that generality, or let's say maybe at least for co-compact lattices. And I think that should be doable. And I should also say that Ben Löwe and Mikołaj Fracik have wonderful work where they study somehow this setting. They don't get results about this that are better than the general theorem here, but they get different statements that are in a different direction much stronger. So let me at least mention their work here. They get something which is, I won't explain it now, but they get statements about homotopy expanders, which are much stronger than somehow this statement, which is a kind of homology expander, if you want, statement. But they get it for very specific groups, namely they get it for octonionic hyperbolic manifolds. But okay, they have, in different directions, they have a lot more stuff, and this is much more differential geometric in its approach. And yeah, maybe I end here. So I think that's a fascinating problem, actually, which should somehow be the geometric counterpart of that theorem and also the geometric counterpart of higher property T for these lattices.